everybody. My name is Andrija Poleksic, and today I'll talk a little bit about relation extraction, about something I've been doing for the last year. So hopefully every model will work, so we can see some results also and learn something about this area of NLP. Okay, I'm gonna share my screen first. Tech support, you can still hear me completely normal, okay?
Yes.
Okay, thank you. Let me just... Okay, and you can see my screen now, right?
Yes.
Okay, can you just notify me if somebody raises the hand? So if somebody has a question, it's not a problem for me to stop and answer them. Just raise your hand and, you know, type it in the chat. I think you can't use, the attendees can't use the microphone, or are they able to use the microphone? Okay. Okay, I think we can start. So as I said, my name is Andrija Poleksic. I'm coming from University of Rijeka, the Faculty of Informatics and Digital Technologies. And I'm the part of the LangNet lab. So we do all sorts of stuff from the NLP area, including from now on relation extraction, which will be presented here today. Okay, and I always start with a simple example because I think it's the best approach to learning something. So we have a simple sentence. Gottfried Leibniz was born on July 1st, 1646, toward the end of the 30 Years' War in Leipzig, Saxony, to Friedrich Leibniz and Katharina Schmuck. Okay, and my question here is, what can we actually induce from this sentence? What is the knowledge that is, so to say, hidden in this sentence? So I think we can all assume here that Gottfried Leibniz was born in the year 1646, or that his mother is Katharina Schmuck, or that perhaps that he was born in Leipzig. So these are just some of the facts that are present in this sentence, some knowledge that is indeed in this sentence. Okay, and if we take a closer look at these facts, the bolded parts here in the bullet points can actually represent some kind of real-world objects that interact with one another. So, for example, the second sentence, Gottfried Leibniz was born in Leipzig. Okay, so we can say that Gottfried Leibniz is one entity that is interacting with Leipzig, and the relation or the interaction between them was born in, because Gottfried Leibniz was in fact born in Leipzig. So with this in mind, there exists an area of NLP, as I said, and it's called information extraction. It is the area of natural language processing, or NLP, that aims to automatically extract structured information, being it the entities that I just shown, for example, Gottfried Leibniz or Saxony, or perhaps the relations between them, and also the attributes that might be present in the sentence, like really old or something, some other attributes, I guess. Okay, so it's still a very, this is a very broad definition of information extraction, but it consists of many tasks, which include named entity recognition, co-reference resolution, and also the relation extraction, which is the main topic of this tutorial, okay? So then another question comes to my mind, and this is, why do we actually want to extract such data? Because if we read the sentence, we were like, okay, now I know this. This wasn't really hard to remember, or it was hard to remember, but I can always read the sentence again. And the main motivation why we want to have automated extraction of the data, of course, is the internet, which is, as we might know it, really a rich source of too large amount of data, being it news, blogs, forums, official documents, so encyclopedias, scientific research. If somebody here is a scientific researcher, he probably or she probably knows how many papers there are published in a single day, how much you actually have to read to stay on top of some research. So there really exists a need to actually automatically structure the unstructured data, such as natural language. Okay, so now we can move to the definition. So as I said, the relation extraction is a task within information extraction, and it aims to automatically recognize relationships between entities, and it can be a relation between more than two entities, and also on one or more sentences. So again, a very broad definition, because different researchers in this area tend to define a relation extraction differently. So based on those bullet points here, it can be defined differently, as I said. So it can have a variable number of entities. We can have a defined or finite set of relations or undefined set of relations. Today we will explore a relation extraction with defined set of relations, because it tends to get really complicated if you have undefined set of relations. It is a really different task, a rather hard task to perform, because you can have multiple relations that represent the same thing, but they are just named differently in a certain situation. So you have a lot of overhead with the data, so to say. Okay. And also we can have marked and unmarked entities. So I talked a little bit about entities. We saw them in the sentences. So the idea is for relation extraction, as I define it here, to actually have our model be familiar with the locations of the entities. We don't want our model here to first find the entities where they're present in the text, and then to classify the relation. And as I said, it can be done on multiple levels, which includes sentence, few sentence, or a document level. Okay, so just another example. We have another sentence. I like sentences, apparently. So the Javan spitting cobra, and so on and so forth, is and highly venomous species of spitting cobra native to Indonesia. Okay, so as I define this task today, the relation extraction, our model has to predict whether there exists a relation between those two entities that are bolded in this sentence, and what would the relation actually be. So the correct answer here is the endemic to relation. So there is a relation called endemic to between spitting cobra and Indonesia. And the results always look something like this. So they're in form of a triple. In the bottom of the slide, you can see it. I don't know, can you see my mouse when I go over the text? Oh yeah, yes. You can. Yeah, you can, because I'm sharing the whole screen. That's actually good. Okay. So the result of relation extraction always looks something like this. It's a triple that consists of two entities which are connected via a single relation. Okay, and let's say that we managed to train our model, and now we can extract relations. We are so powerful with it, and we get a lot of triples that look something like this one presented. And what do we want to do with it? Because if we just control find or something like this is not really useful, I would say. Well, this is actually where the knowledge graphs step into the play. So relation extraction is mostly done to automatically construct such structures as knowledge graphs. So this is a knowledge graph that is based on the first sentence. So we can see that if I go back a few slides, so we had entities such as Gottfried Leibniz, Leipzig, Saxony, Leipzig again, Katharina Schmuck. We can see that they are here represented as the nodes in the graph, and the relations between those nodes are represented with the edges of the graph. Okay, So in this form, we can do a lot of stuff. We can query it. We can say, okay, find me a node that has a relation born in and also continues with the relation state off to some other node. So it is the most important thing, and it is that the knowledge graphs are can be interpreted by the computer, so they can be queried, they can be built upon, and so on. And also, I added here another node, Friedrich Leibniz. He was present in the sentence, if you remember. So we know that Katharina Schmuck is the mother of Gottfried Leibniz, and we know that Friedrich Leibniz is his father. So we can probably conclude that they're in some kind of relation. We can call this relation spouse. So the idea is that other than we just build upon the data that is present, we can induce some new things. We can, for example, find out that if we know that Saxony is in part of Germany, we can then conclude that Gottfried Leibniz was in fact born in Germany. Okay, this is not a really big problem for us because we already know that Saxony or Leipzig are in Germany. But if you have a lot of data, for example, 100,000 papers or 100,000 news blogs, whatever, then you can find some knowledge that is perhaps hidden or just hidden in plain sight, so to say. Okay, so this is the main motivation. Why would you use knowledge graph? And of course, automatic construction with relation extraction is not the only method how to build a knowledge graph. You can in fact do it by yourself. You can just denote all the data and gather through crowdsourcing such graphs. So one of these graphs is actually Wikidata. As it says here, it's a free and open knowledge base or a graph. And it has somewhat similar model to the knowledge graph that we explored here. So it consists of items, properties, and values, where the items actually correspond somewhat to the entities in most of the cases, and the properties in the Wikidata somewhat correspond to relations. There are around, I would say, 12,000 property types in Wikidata. Of course, there are many of them that are really similar or aren't useful for us. And the values here can be either entities or attributes. Okay, I would actually like to visit this. Let's not continue. Let's not finish yet. Let me just show you here. Okay, so I probably. Okay. So I just wanted to show you how the model actually in the Wikidata case looks like. So it's really similar. For example, we have a relation here between Earth and Mount Everest, and the relation is called highest point. So it is something to keep an eye on because, in fact, if you want to do relation extraction, you probably need some already existing graphs so you can train your models, of course. Okay, and if I go back to the presentation, sorry. Where are you, my presentation? Okay. I will just leave it like this for now. Okay. And also we can find out the list of properties, but I will leave this to you if you are interested in, or perhaps will be interested in relation extraction after this tutorial. So you can explore the relations that are present there. Okay. And now I would like to move to a little bit more practical part of this tutorial because theory is fun and everything, but I think training the models is a little bit more fun. So I'll give you this link. Sorry. I can copy it in the chat. It is also present actually in the files that can be downloaded, that tech support put in the Mm. Okay, here. Are there any questions for now regarding the theoretical part of relation extraction, or we can move on to the practical part?
You just need to put that you are sending to everyone, not just host.
Okay,
Yeah,
thank
yeah.
you. No, not to you. I have just those two, how to say?
Then I can share it.
Okay. Then I will send it to you here. And you can then proceed to share it to everybody. Okay, here is the link. So if you want to follow what I'm doing in the rest of this tutorial, it can be accessed via this link. It should be working. I will try it also, just in case. Okay. Seems to work pretty fine. I already loaded it here, so you can, everybody, if you want to follow my pace, you can open Google Collaboratory, or we will call it Google Colab because it's really a tongue twister for me. So can I get some response here? For example, can you raise a hand if you're going to follow the tutorial with me? So just so I can know that to slow down or something. Okay, thank you. Thank you, tech support. You're the biggest support. Okay. So you would, if you're following, upload the notebook that you just downloaded and found it on the computer. Okay. And then you would have something that looks like this. If you are familiar with Google Colab, okay, super. So first, I would like to share a few thoughts about this library that I'm using today. That it is actually a showcase of this library from Tsinghua University. So the library is called Open Neural Relation Extraction, or OpenNRE. And it serves as an important repository for somebody that is trying to do relation extraction, or perhaps trying to get to know relation extraction as such. So you have a much of data set information and so on here if you're interested, and also the basic definition and so on. So I will first connect with T4 GPU, so I can train my models. Of course, you can join with the CPU if you have already used the time today, because Google recently blocked me also. So yeah. Okay. Then we can get this repository to our Colab. Okay. And tweak some of the versions. Of course, as it always happens, you have to deal with versions, because here in Colab you're using actually Python 3.10, and this library is supported for Python 3.8 if I'm not wrong. So I had to do some tweaks to the requirements so we can use it. And now we can finally install everything we need, so including Torch, transformers, PyTest, protobuf, and also a Flare library. It will take around 1 minute, so not too long. Okay. Now we have installed all the libraries that are necessary for this framework. And we'll finally install the framework now. Okay. So now we can actually show a simple example of it if I manage to scroll to the end of this output. So we just import the library as usual in Python. So this is the example that is actually present on their website. Is the first example you will see here. Nothing really special, just to check if everything is working correctly. So we can see we have a text. So he was a son of Mael Duhon, or however that is pronounced. And grandson of the High King Ed. I'm too afraid to pronounce this. And we have the positions of the actual entities in the sentence. And our model here predicts a further relation between entities. Let me just, between 18 and 46. So I would have to count it right now, but I guess it's a mild one. And King I'd. Yeah, okay. So it is a relation between the model is classifying the relation between mild one and King I'd. Okay, and it says with 75% confidence that it's a relation called father. And if we check the sentence again, it in fact is. So I think everything works just fine. But I think it's boring to just use already trained models and see their results. So I prepared something for you to work on. So my idea was to use the data set or the database that was provided by Shimurina and other contributors. So the idea of this database is actually to connect existing data sets and pre-process them in a way they can be used for relation extraction. So we have some of the relation extraction data sets listed here that were in fact connected into this database by Shimurina. So those include FuRel by Han et al., T-Rex, DocRed, Wikifact, Wiki20m, and WebRed. So those data sets are all used for relation extraction, but in different scenarios and different definitions of relation extraction. So for example, DocRed is a relation extraction dataset for relation extraction on documents. Wikifact is for factual checking. Wiki20m is for sentence level relation extraction. And FuRel is, of course, few shot relation extraction. I think it's also on the sentence based, but it could be bag level. Okay, and here you have some of the statistics of the data sets. So we can see the two biggest ones, Wikifact and T-Rex, that contain also a large number of types of relations. Let's say you want to model some kind of data, you need to first find out what relations you actually want to extract, because if you are talking about, for example, protein interactions, you probably don't need a relation that will be called mother of or something like this. You need relations such as monomer of or relations that are in some other form characterizing some chemical reaction. Okay. So as I said, Shimurina's idea was to connect all these data sets and pre-process them into a unified database, which now contains 47 million examples of sentences and contains over 1,000 relation types. So just to visualize those relation types, that's what I forgot. Sorry. these are just some examples of Wikidata relations. So you have, for example, a relation that is called place of birth. You can have that relation, of course, between some person and a city or something like that. So you have the descriptions for those relations. And if I scroll down, you can see there are many, many examples of relations, actually. As I said, around 12,000. Of course, they aren't all useful. So in this case, there are 1,000 relation types. And if we observe the last column here, it says, it talks about percentage of negative examples. So in before the transformer models, actually, it was necessary to first classify if there actually exists a relation. So you would have a sentence that contains, for example, two entities, and the model had to predict if there exists a relation. If not, he says, okay, no relation. Else he says, for example, unknown relation, or the relation that actually is. So it is important to model that part also into the data set, because in fact, in the sentences, there are many entities, and between most of them, there actually isn't any relation present. So our model, in this case, has to learn negative examples that contain entities that in fact don't have any relation between them in the sentence, and also have a relation that is perhaps unknown. So this is also the part of negative relations. Okay. So I wanted to try a simple example here today with you. So as I said, with using this unified database, I queried it to filter it to those 5 relations. I wanted to actually model family relation dataset. So it consists, in this case, of 5 relations that are called no relation, unknown relation, father of, mother of, and sibling. And with these 5 relations, I would like to try to model some text to see if we can, in fact, get something that looks like a knowledge graph. Okay. And why is this all possible? Well, all of these data sets were built on the distance supervision assumption. For example, T-Rex. Let me just open it. So the idea of this is, okay, we have a lot of data on Wikipedia, and we have a already crowdsourced Wikidata graph. So let's take all the texts and find all the entities in the text of Wikipedia, and let's extract all the pairs of entities in the text and compare them to Wikidata relations. And then if something similar to the relation name is present in the text, then say, okay, we can assume that there exists that particular relation between 2 entities in this sentence. So this is a distance supervision assumption when we are talking about relation extraction. And it's a really important method because it can give you ability to build data sets based on different languages. So Wikidata is multilingual, Wikipedia also, so you can perhaps make a relation extraction model, in fact, for I don't know, Croatian or German, and so on. So you can adjust it to your needs and train the model according to it. But in this case, we will stick to the English because there are already present data sets, and it's easier to work when you don't have to pre-process everything and do literally everything. Okay. So back on track, as I said, 5 relations. And then we filter the whole database to find all the examples that have actually those relations that are of our interest, to create a data set for training our models. Okay, and this is what I did. I spared you of SQL querying. So here is the manual download link for the dataset. Also, you can just click on this code to execute, and you will soon have the data set present in a CSV format in your data folder. Okay. So now we can move on to the pre-processing of this data set, so it can fit our model. We'll load some standard libraries such as pandas and the relation regex, and also the tokenizer for tokenizing the sentences. Okay, and this is how our data looks right now. So this is loaded from a CSV that we just downloaded. So we have a relation ID, we have a relation name that is unknown for the first few examples, but okay. And then we have a sentence, and also, sorry, let me minimize this, okay. And also the name of the first entity and the name of the second entity here. So if we observe this sentence, on 10th of November 2017, French President Emmanuel Macron and German President Frank-Walter Steinmeier inaugurated the new memorial. So our model here has to predict actually that there isn't any relation between German, which is a subject, and the object, which is Frank-Walter Steinmeier. So this is also a problem with relation extraction, but because different researchers come from different areas of computer science or perhaps linguistics. So in this case, our entities are denoted with subject and object notation, which actually corresponds to a relation that actually corresponds to the names that we'll use here. So we want here to have something that looks like tail and head, not like object and subject, because this will be actually the input to our model. Okay, so the tail corresponds to the object, and head corresponds to the subject of the sentence. And the predicate is usually the relation, but it doesn't have to be the case, of course. Okay, so we need to get from this sentence and this information to something that looks like this. So it contains a tokenized sentence on a word level, of course, and contains information of the location of the tail and head entities in the sentence. So the tail entity, called Old Trafford in this case, is located on this position, 19 and 20. And if we count it, we will see that, in fact, here is Old Trafford in the list. Let me just check if I can, for you to see more clearly. Okay. So this is what we want to get. And for this, I created a few functions that I won't go into detail, but so they are remove SO brackets to remove the subject and object notation, because of course we don't want our model to be trained in a way that in the sentences that contain subject and object. We want to clean this data because it isn't necessary, and it won't happen in the real world examples, of course. Then we have a function that is called tokenize. So it is standardly implemented in OpenNRE library. I just imported it, and extract head and tail token and tokenize. So this is the function that actually calls these two functions all together. So, okay, I think it's the best if I don't stick too long on this, but so the idea is that we have a string sentence, as I said, which contains subject and object, and we want to finish with a sentence that contains a different notation. Those special tokens that I call the head start, head end, tail start, and tail Z as also tail end. So these tokens should denote to our model, okay, or to our pre-processing step, okay, here we have the subject entity, and here we have the object entity. So I made the verbose example of this functions, so you can see actually the process of them. Let me just load those functions. Okay. Okay, so we first had a sentence that looked like this. So Yansa, as in Yoruba religion, commands wind, storm, and lightning. And we wanted to remove all the occurrences of object and subject notation. And we are left with something that looks like this in the end. So instead of having object and subject, we have special tokens, tail start and tail end in this case. Okay. And then we want to tokenize the sentence. So the idea of this tokenizer was to have some special tokens that would not be tokenized, but it doesn't work as expected because something is wrong in the code, obviously. So I had to reconnect those tokenized parts, but that wasn't such a problem. So the idea is to have a clean tokenized text and also the information on the location of the entities. So in our case, as we know, the entity was called Yoruba. So if we visit this location 4, so it's 1, 2, 3, sorry, 0, 1, 2, 3, 4. So in fact, Yoruba is located on the location 4. So it doesn't span on more than a single tokenized part. Okay. And then we want to apply this function to the whole data set so we can have tokenized sentences with the correct locations of our entities for our model. This will take approximately a minute and a half, so I can move back on to the functions. If there is something else to be said here. Oh, I think it's already, no. Okay, are there any questions now, or is everything clear for now? Q&A is empty. Okay. Anything in the chat? No. Okay. Okay, now we apply this to the whole data frame. So the idea was, okay, let's tokenize. I'm repeating myself. So let's tokenize the sentence and also remove the subject-object notation, and in the end, find out the location of the entities based on the spans. Okay. And so based on this, we get 3 new columns that we'll call a sentence tokenized because it represents a tokenized sentence, and also head and tail information that contain locations of the entities. And then we'll join that back to our original data set. So we have 3 new columns actually. Okay, so as I'm not really a master of programming, and the data is in fact not really clean, because one, it's gathered through distance supervision, and 2, it's modeled in a way that it contains examples that actually shouldn't work. So there's much to do. So in some sentences, it happens that you have multiple subjects, or perhaps you have, for example, subject that is also an object that is also a subject, something that I think I prepared. Just a second. Let me just view a few examples if I can. Okay, so as I said, it sometimes happens that we can't locate the entities from the sentence, so we get something that looks like, for example, the second sentence here for geographic and demographic information of the village. So this contains multiple object instances, 3 of them, which is something that we actually don't want to use because we do a relation extraction on just 2 entities. So obviously we have some errors here, which is why we want to actually remove all the data that isn't useful for us, such as this example with multiple objects, or some other example with multiple subjects, and so on. Okay. But if at least one of the entities is correctly located, such as in this case, so Reynolds Country object Missouri was also named his honor. So this sentence has some wrong inputs in the beginning in the original database. So it's our model here is supposed to know that his actually refers to Thomas Reynolds, which is of course impossible. So we want to keep this relation for our model to generalize better, because at least the tail entity here is in fact correct. Okay, so we want to actually remove all the sentences that have wrong locations of head and tail entities both. So we'll do this in a second. Okay, there is in total 15,000 of them from the 102,000 examples that I prepared. And we have 28,000 sentences that have unmatched either tail or head entity. Okay, but so 13,000 of these examples is still useful to us. Okay, so we want to remove all of those that are actually not of our interest, and we can move on to the train test split, or the training part of this tutorial. So I will take a quick break of 3 minutes for you to follow me up if you are actually doing all this, and just to prepare the rest of the tutorial. Okay, so see you in 3 minutes, then I will continue. Okay, so I see a lot of requests for the Dropbox that I shared the link to. I guess I expected it to work without me approving all all of the accesses to the Dropbox actually. So I'm really sorry for this. You can still. That means that you in fact maybe can't. Okay, just a second. Maybe I can rearrange the settings regarding the availability of things that I share. Okay, so has anybody actually managed to download uh, the notebook or some of the data? Can you write it again in the chat, or perhaps raise a hand if you have a problem with this? I would be really sad, huh? Okay, right. I agree with the Dropbox, but the problem might appear if you try to fetch some other data from the Dropbox and it doesn't work, because I actually connected some of the parts that I will show from the Dropbox. So in fact, if that doesn't work, let me you just follow me for now, and I will make this links available to everybody, or later on share with the attendees in the link or something like this. Okay, so I think we can continue. I'm really sorry that you can't access the data. It wasn't planned, but Dropbox has some other plans. So I will continue now with the train test split part. So the problem might appear also when you try. Okay, maybe I can just ask this one more question. So can anybody actually make this one from the beginning work? So can anybody get this content that is present on this link from Dropbox? Okay, let's say I answered it live. Okay, thank you very much. So if you are already can download notebook from the Zoom, then there is no problem, because the rest of the tutorial is actually based on getting the things directly from the notebook. So we can continue. So if somebody is following, I'm really happy. Okay. So let me just go back where I stopped. Okay, so we cleaned the data. Again, if you later try to review this code, you will see that some of the parts are actually not really well written, but the point was for you to see the whole process of actually building the data set and then training the model. Okay, so after we cleaned those entities, or the sentences that had no located entities, we are left with the data set that contains roughly, I would say, 90,000 examples, of which 20,500 correspond to unknown relation, and some other have a little bit less of the examples. So the unknown was the only one that had no problem when pre-processing the data set, actually. So this might also be the problem, because if you're not really careful with the metrics that you use, your model could be trained in a way that it performs the best, of course, on the unknown, because this is a little bit of imbalance in the data set. But hopefully, if we use F1 metric with macro averaging, I think, then we wouldn't have any problems, because this metric takes into the account the disbalance of the data set, and in fact makes all the relation, no matter the counts of the relation, equally important to learning. Okay, so for the splitting of the data set, we will use implemented method called train test split from scikit-learn library, and we will get the train data that contains roughly 70,000 examples with 9 columns for now. And then we will proceed to make test data and also validation data. So this is just the print to show all the statistics of the data set. So in total, we have 70,000 examples for training. For validation, around 4,400, and test data of 13,000. And all the data sets, as you might expect, have all 5 types of the relations. So no relation, unknown, father, sibling, and mom. Okay. And the data was split for training was 80%. So the test data was 20%, and then the test data was split in a 75-25 ratio. Okay. And I just left the random state of 42 everywhere, because it's the default in this library. So it is important to use something like train test split, of course, so you mitigate the chance of training your model on just one relation, because if you use this stratify option, it tries to balance or to produce the train and test and also the validation data sets in a form that corresponds with the ratios of relations present. So the idea is to have similar ratios of appearances of those relations in all the data that we would use for training and also for testing and validation. Okay. And now we will make the data set as an input to the model. So as I said in the beginning, we have to get something that looks like, like just should have put it again later, but okay. Something that looks like this. So tokenized sentence, tail information, and also head information. This is not the important part when we are dealing with inference, but also the relation ID and the relation name. So something that looks like this in a JSON format, actually. And for now, we have to split the data into 3 data frames. So for this task, we will use and also we need so to say a cheat sheet for the model that will represent the classes that our model has to classify. So in this case, it will be so content OpenNRE. Benchmark. Okay. So in this case, it will look like this. So 0 will correspond to the father, 1 to unknown, 2 to mother, 3 to no relation, and sibling to 4. Just to encode the data on training, okay? And then we can move on to building the data set. So as I said, in the JSON format, so we have a token that has a tokenized sentence that we cleaned before, and the tail information. Were there any questions or something? Just a second. Okay, still nothing in the chat, okay. Sorry, I just minimize this so it doesn't bother us. Okay. So we have, so we need to get something, as I showed earlier, something that looks like the example. So containing sentence that is tokenized, information about tail, and also head entity, so their positions, and also their names for inference reasons. Okay. And then we move on to actually writing this to text files. So the input to the model, that's why I prepared this part. I will also run this. So those are actually the commands that were present in one of the examples. So the idea is to have a similar structure to something that the creators of the library or the framework OpenNRE imagined to have. So this is how the input to the model looks like. It has its tokens. It has head information again and tail information in the end. Okay. So with the write text function here, we've done the same thing. So now we have a folder that contains a mapping to the numbers of the relations, and we have test, train, and validation data in the form of JSON files that will be loaded in our model. Okay, and then we can move on to training, hopefully. So for this, we have to do some adjustments. I will use the existing example here. So train supervised BERT. So the framework actually has some examples which contain test multi-label BERT, test multi-label train back BERT, train back CNN, and also train supervised BERT that is here of our interest. And what we need to fix is add our data set to the choices of data sets. So by default, you have these choices. And if you do this, the data sets are automatically downloaded, and you can start your training in like 5 minutes. To make it harder, we made our data set, which is called family relations. So we'll add this line or this to the example. So you just need to find it into the code. And add it to the choices that are present in family relations. Okay. I will leave it a little bit more. So it's right under the hashtag data line 35. You just add family relations to the list. And also, since the library has its automatic download for each dataset that you choose, we would have to implement automatic download. So, of course, we won't do this. We will, in fact, just make a way around it with this line. So in line 75, we will add a simple if that says, okay, if we are not dealing with the data set we just made, then do the automatic download, else please don't download anything. We already have everything prepared. Okay, and then we can, okay, I can actually show you all the other things that you can tweak around. So you can change the checkpoint that you would use for your model. I will use birth base uncased from Hugging Face library. Also, here are two possible choices for the pooler. So I won't go into the detail with this thing, but it's based on the research paper called Matching the Blanks, where you have a few examples of relation extraction, and you can use a CLS token of the bird model, or you can use the entity markers of the tokenized sentence. So, as I said, not to go into the details, you can read the paper if you want, but in this case, we will use the entity option. You can just do the tests on the model. We want to train it for now. And you can use mask entity, which actually hides the entities from the model. It removes the location data, so the model has to first find out what are the entities and then classify the relation that should or shouldn't exist between them. And you can do some choices regarding data. So you can choose the metric. As I said, we will use micro. Sorry, I said macro, but we will use micro F1. And we also have the accuracy option, but it's not really good for unbalanced datasets. And also, you can choose where are the locations of training data, validation data, test data, and relation to ID file, which is the this file here that we made. Okay. And some hyperparameters. So if you don't have a NVIDIA GeForce 3060, you probably want to lower this batch size to something that is something of a reasonable, for example, 16 or 32, and maybe play around with learning rate or a maximum length of a single sentence, which of course puts more pressure on the memory of the graphic card, and also the number of epochs that you want to train your models, and the default seed 42. Okay. So in my case, I will use the pre-trained mask language model called BERT. So BERT base uncased. It's present on the Hugging Face library. And I will use the dataset that we made and train, for example, for 2 epochs, and put my seed again to 42, and use the batch size 32. And also I want to save the checkpoints that I train to the, okay, so like this, to the checkpoints folder. Okay, I will just run it, and I already did the training, so you don't have to wait for 40 minutes again. But just to show that it actually works after some downloading. Okay, everything is working great for now. The checkpoint folder was just made automatically. So you would have checkpoints here. And you start the training that for a single epoch, when we talk about this data set, takes around 22 minutes. So it's not really long. And after 3 epochs, you can have a model that works perfectly fine for simple tasks such as extracting relations such as father, mother, and sibling. Okay, I will stop this now for good. Let me just check if it will actually start, because it seems for now that it has some problems. Oh, I'm not using the GPU currently. Yeah, so this will take much longer if you're not using GPU, but hopefully you can just use it. Okay. So let's say that we trained our models. We first want to make the folder called checkpoint. If it isn't actually already made, and it is, but okay. And we want to download again from Dropbox, but automatically pre-trained or trained checkpoints for BERT model that I trained earlier. Okay, so now we have checkpoints for the model. You can, I think this part was added later, so you don't have this in your notebook, but it's more or less the same model. So I just want to show you how it looks in the end, okay? So for this, I was searching for some examples that could exemplify some relations such as mother, father, and so on from the texts. So I searched through a really important source when you're dealing with text, and this is the Gutenberg project. So here you have all the books available that are no longer under any how do you say it, any license, so you can use it for free, and it's everything is open source here, and so on and so forth. So I found some examples like this one. Oh, it's really hard to read it like this. So this one is called 13 Years at the Russian Court, and hopefully we would have some sentences here that contain some information about somebody's family relations, and in fact they do. So we can use this example, and we want to load it into the a single string called text. Okay, so now we have a whole book that is in a single string called text that we just downloaded from the site. And first we want to split it into the sentences, and also then find out all the entities that are present in the sentences. So for this task, we will use the library called Flare. You could use also any other library, but Flare seemed functioning to me. It has a good support. It also has implemented a lot of things that are useful for NLP area. So I would highly recommend for you to, if you're using or trying some NLP, to actually visit this site and Write library from Humboldt University of Berlin. Okay, and they also have implemented the named entity recognition model that we will use, so to recognize our entities. So as I said, first we split the whole string into the sentences here. And then I simplified the task here. So I said, okay, if there is one of these words present in the sentence, then use this sentence for the inference to show the model, else just ignore it, because it would take a lot of time if we went through the whole book and only every 100 sentence actually has some importance to our relations here. Okay, so I already ran the script, and we have now 129 sentences, for example, and they are already they already have marked entities, which can be organization, person, location, and so on and so forth, from the Flare library. So what we want to do is, for all the sentences, extract all the pairs of entities in this sentence that were found out, and construct our data based on this. So we have, for example, this sentence: the Grand Duke Michael arrived with Kerensky and had an interview with the Tsar, who was delighted to see his brother again before his departure. So here the recognized entities were Grand Duke Michael, also the Kerensky, and the Tsar. And we want to explore all the combinations, or let our model classify if there exists a relation between any of these combinations of entities. And we do this for all the sentences that contain father, mother, or similar words. So I will just make the input into a data frame. So I used again the same function as in the beginning, the function to clean the subject and object notation if it is present. It isn't in these sentences, but we still want to add head and tail notation for our model to find out the location of the entities. So we have now the location of the tokens that correspond to the entity, which are here 6, 9, and 15, 17. We can see it even in the interactive. Oh no, it looks terrible. Never mind. We'll put it just like this. Okay. And this is just the step for loading the data, actually. So our data now for the inference of the model. So we trained the model and we want to see how it works on the raw data. It looks like this. So we have tokenized sentence and all the combination of the same sentence with the different entities that are important in this case. So in one case, it will be Duke George of Württemberg and Eugene there, and so on. And based on this, we will do the inference on our model. Okay, so I prepared actually the test supervised BERT scripts for you to use. So the idea is that to mitigate the need for, again, twinkling with the code here. Where is it located? Example, test supervised BERT. Okay. So if you took your time and compared it to the train supervised, it's actually the same thing with just a little bit add-on in the end. Okay. Let me just move to the end. Okay, the only difference is that we automatically here make our data look as the input that is needed to the model. So it contains a sentence that is tokenized and also the information of head and tail. And we do that for both combinations, in one case where the first entity is head and second tail, and the other vice versa when the first entity is tail and second entity is head. Okay. And I just found out that I also need to add this to load the actual checkpoint here. Okay. So from line 117 to line 135, you add that to the script that you just downloaded. Let me just check if there are any questions. Q&A seems good. Okay. And chat seems also okay. Are there any questions for now? I'll wait a minute or two, and then I will continue with the example. Okay. So as I said, I just noticed that you actually need to load the checkpoint here. So this line 135 says, okay, load state dictionary, and it loads the checkpoint that you trained, that we downloaded before. So we'll just add this here in our definition of the model. So I just added this part where the framework that is built up on the OpenNRE library allows the checkpoint, okay? And then we can classify the data that we prepared. It would take around 4 minutes because there are actually it's actually not working on the GPU when you're doing inference in a way that you can see the results. Okay, I have some problems. Just a second. Here it is. Okay. Why is there a problem? Sorry, I didn't see it, but I don't have any more. Google doesn't let me to use their GPUs, so there pops up an error that says, okay, you're not using a GPU, but you're trying to execute a script that actually uses it. But this can be fixed easily. Let me just check the error again. I will not take longer than a minute. And let me just okay. So in test supervised BERT, I will add the line that it suggests. Sorry. Okay. This will be a little bit harder, I think. I'm really sorry for this. It was working well on GPU, but of course, something had to happen. Okay, then I will skip the trained example, but you can try it yourself. So you just need to run this and you will get some results, and you would then try to visualize it with the NetworkX library. But in this case, since I can't use the GPU, I will just adjust my, not this one, I will adjust the script accordingly. So I will not use the code that I just added. And I will use pre-trained model. So just check. Okay, this. So in your case, you can probably still use the GPU, so you can do the task with the actual model that was trained. But I will use here the pre-trained convolutional neural network model for extracting relations, just to show you the example of what it should look like. Okay, and if we visualize all the triples that are stored, sorry, right. So this is the output of our model. As we said in the as I showed in the beginning, we had an entity and then the relation between the entities and another entity, so triples, and we have a lot of them here. So we can visualize them with the NetworkX library that is actually developed for the network analysis tasks, but it can also do some simple visualization tasks. So we get something that looks like this. So this is in a form, a knowledge graph of the whole book that we just put there casually, and it is now available here. And hopefully the model did a good job and classified the relations correctly. But because this is a book that nobody has read actually, it is really hard to tell if this model actually works good. So for this case, I actually used none other than ChatGPT, of course, to make me a simple text, which can be easily proofread. So we have a simple story for a 3-year-old child, which is represented by our model here. And we will just show the same thing on this text. Okay, let me just make a new file. Let's call it GPT lore. Okay. And let's add text to it. So this was generated by ChatGPT, and it's a simple story about a simple family. So about Lily Aurora that has a father that is called Sir Arthur, and so on. So we can actually check if our model does a good job. So I will go a little bit back and do the same thing that I did for the book here with the ChatGPT generated text. Okay. Okay, so again, splitting the sentences, we have 5 sentences. This is not really a lot. And we already tokenized them and find out all the entities. So in this sentence, we have entities such as Lily and Arthur. In other sentence, we have a lot more entities, but we'll check it with an example. Okay, I'll just delete this one because okay, this is how the input data will look like. And then we can again do the inference on the model. And visualize the results. Okay, and we have something much simpler than the previous example. So we can see a form of a knowledge graph based on just the few sentences that ChatGPT actually generated. So we can check if they're actually correct. Let me just remove if something is unknown. Okay, so our model here predicts that the Lily is the mother of Arthur, so we can check that in the text actually. Once upon a time. Okay, our model doesn't work really great because Lily is obviously not the mother of Arthur, but it is the other way around. So it classified, if we observe it a little bit closer, it actually classified the relations both ways. So it said, okay, Lily is the mother of Arthur and Arthur is also the mother of Lily. But if we think about it a little bit more, Arthur in the sentence was actually a father of Lily. So classifying the relation as a mother in this direction is actually correct. So it's not the best model because here I'm using the CNN model and not the BERT trained. But you can actually see what you get when you use relation extraction. So you get something that looks like this, but much more complicated. And then you can query the data, you can find out all the information that is hidden and so on and so forth. So with this, I think I will actually end the tutorial because I showed all the examples that I wanted to show. If there are any questions, I'm happy to answer them. If not, that's it from me for today. Okay. Thank you for your attention, of course.
Thank you, Andrea. It was very interesting, and thank you everyone for watching the tutorial. So, bye-bye.
Goodbye.